Hello, Physics AP peeps. It's Mr. Martin here, Marty, all that stuff, all the other nomenclature that I have. So what we're doing here is we're doing a lesson on curved mirrors. So if you weren't here, you're watching the video because you owe me this assignment, and rather than wait for office hours, you should be able to follow along and produce what I'm asking you to produce when we investigate the ray model of light. So again, what we're doing here is we're using the ray model of light, which assumes that light is a ray. And what we're doing is constructing images using the ray model of light using curved mirrors. So when you look in a curved mirror, like a cosmetic mirror in your bathroom, if you look in real close, you'll notice that you have a magnified upright image. But what you probably never saw was that if you pull that curved mirror back, you eventually will see a blobby image, and then you'll see an image that's upside down. I will, in this document where you're finding the link to this YouTube video, I'll try to find some other images of curved mirrors in action. But for right now, what we want to do is employ the ray model of light in order to create images in curved mirrors, or called concave mirrors, at different points. So if I put the object here, what's it look like? Put the object here, what's it look like? If I put the object in another spot, what images do we get? So what you need to do as an assignment is you are going to recreate the ray diagrams that I am doing for you right here on the paper. You need to do the same thing exactly as I describe it. And then at the end, I'm going to ask you to make some measurements on your own. I'm going to ask you to do some calculations on your own. You must do this video first before you do the other three videos, right? There's some setup that's involved here that you're going to have to use in the next three videos provided on what you have to do, okay? And again, you can, whatever you owe me, you watch the video that you owe me. So when we're starting out here, we have a piece of paper here, have some stuff lined up, and I put a horizontal line across about the middle of the paper. It doesn't have to be measured, but somewhere around the middle. When you have a curved mirror, you have to imagine that a curved mirror is like someone took a sphere and cut a slice off the end of it. So you have this mirror that's curved like this. So in that regard, that mirror has a radius. So the radius of a curved mirror, concave mirror, that's a concave mirror. You can think of it as the radius of that mirror is considered the center of curvature. So what we need to do is, in order to do this properly, you have to measure everything. So what I'm going to do is I'm going to put a dot to represent my center of curvature right here in the middle of the page. I'm not necessarily measuring it, but somewhere in the middle is fine, okay? This is an axis. This is an imaginary line on which our mirror is going to sit. It doesn't represent any physical boundaries. Now what we need to do is draw a circle with radius 10 centimeters. So up here, you'll notice in the top, I have established that the center of curvature of our mirror is going to be 10 centimeters randomly. How are we going to do that? Well, we actually have to draw a radius or a curve that has a radius of 10 centimeters. So I don't like using drawing compasses. They suck. So what I'm going to do is a little bit ad hoc, a little bit weird. No, I'm going to kind of come up. Okay. So what I'm going to do is I put the 0 mark here on the ruler, and I'm going to put a 10 centimeter dot, a dot over here at 10 centimeters. And then all I'm going to do is keep that 0 at 10 centimeters. I'm sorry, this end at 0. I'm going to put another dot at 10 centimeters. And I'm going to do the same right here. And I'm going to keep doing it around. This is a lot easier than going and buying a drawing compass. And most drawing compasses are frustrating to use anyway. So here, hold on, dropping stuff and picking up. And so what I can do now is I seem to have these dots. And what I can do is, doesn't have to be perfect, but we're going to freehand a line through all the dots. So this is some preparation that I've already done in the other pieces of paper. But this is, I'm showing you how to do it, which is why you have to do this video first. This we're going to call C. Now we're going to employ one of the most difficult formulas in physics. The center of curvature is exactly half, the focal point of this mirror is exactly half the center of curvature. So very difficult. 10 divided by 2 is 5. I know, it's crazy. What is a focus? Well, it's different than the center of curvature. If you've ever played with a magnifying glass, even though that's a lens and not a mirror, it's the same idea. It's when light comes into a mirror, it wants to bounce off that mirror in accordance to the law of reflection and go through, all of those rays want to go through a point, and that point is the focus, right? So what I'm going to do is, since the focus is 5 centimeters, I'm going to put my ruler down. Notice that's at 10 centimeters, and I'm going to put a dot at 5, and I'm going to label that F. Easy as that. while we're here, I might as well note that all measurements made, and you're going to have to measure stuff, assumes that where the mirror meets the axis, that is 0, and all distances will be measured from 0 to here and from 0 to there, or wherever the object is. So again, that's going to be our 0. The other thing we want to note is this is a concave mirror. We expect to see images on this side. So if this were a mirror, this side's silvered, that's silvered, sorry. This side's silvered, that side's not. So we expect light to bounce off and be on this side of the page. We don't expect light to go through the mirror and end up on the other side. That doesn't make any sense. So in terms of our nomenclature, in terms of our coordinate system, we're going to go ahead and call this side of the mirror positive and this side of the mirror negative. So if any distances that we measure that are on this side will be positive distances, any side on this side will be negative distances, just in terms of our coordinate system. Okay, now this is also in the document. We are just about ready to do our diagram, but we need to put an object in front of the mirror. As we mentioned before, where you place the object determines what image you're going to see. So what I have done, if you come back over here, I am going to place an object 12.5 centimeters away from the 0 point. So coming back to my ruler, again, notice I'm measuring everything out. It matters, believe it or not. You know that I'm not big on precision very much. Like I kind of go, around it, it's close enough. This one you actually have to measure out. So I'm going to put an object here. I'm going to call that DO. This is distance to object. I have said randomly that it is 12.5 centimeters away. And I'm also going to place an object at DO. I'm going to make that object an arbitrary length. So what I'm going to do is I'm going to make an object that's 3 centimeters high. So I have HO here. That's height of object is going to be 3 centimeters. So I'm coming back to DO. And I'm going to draw an arrow 3 centimeters high. Now the reason we're using an arrow, because it's the easiest object to draw. We're eventually going to draw the reflection of this object in front of the mirror. We don't want to do something complicated, so I'm just going to choose an arrow. This is not a vector, it's just an object. Okay, now we're ready to go. As mentioned in the document that supports this video, if you're going to do anything in geometric optics, and you'll see in a minute why we call it geometric optics, a lot of geometry is going to happen. I forgot what I was saying. Hold on. Wait, it's coming back. This is me in classroom too. I forgot. Oh yeah, okay. So in the document that supports this, when we're doing geometric optics, there are obviously an infinite number of light rays coming off of this object. In fact, it's a model, so it's not even the truth. So it's either an infinite number or none at all. Who knows? But we're using the idea that light is a ray to reconstruct this object as an image in this mirror. You need at least 3 rays to define an object. Not 2, not 1, but 3 rays. And those rays kind of follow this pattern, and as you saw in the document. So what I'm going to do here is I'm going to draw the rays in a different color. I suggest that you use a different color. If you can't, that's fine. Okay, again, reminder, your job is to recreate all of this on your own with rulers and proper measurements, and it's up to you to fill in the rest of this and fill in the rest of this. Okay, this is the science behind all of this, right? Okay, so first ray. The first ray in a ray diagram is the one that comes, this ray is going to come off the tip of this arrow. So all of our rays are going to come off the tip of the arrow. First ray goes parallel to the axis, bounces off the mirror, and goes through the focal point. I'm going to say it again, parallel to the axis, hits the mirror through the focal point. So I'm going to draw that line right now. I'll try to go as parallel to the axis as I can. Actually, let me do it like this so I can see. Again, I'm doing my best. You really want to try, you know me with detail. It's not really my thing, but I know I'll get better results if I try to make it as parallel as I can. So here's our first ray. It hits, I already know it's a little too high. That's the best I'm going to get it. And if I had a clear...
They could measure.
Yeah, they can measure it.
Make it more accurate.
Yeah, I don't want to bore you with measuring it. But yeah, you can figure out a way to get as perfect a line as possible. It's going to bounce off the mirror, go through the focal point, and notice I'm drawing that as long as I can. There's our first ray. I'm going to label that ray 1 and ray 1. Okay, next ray. It's going to sound, it's the exact opposite. This ray went parallel to the axis through the focus. The next ray is going to go through the focus and then parallel to the axis.
Do you want a different color?
Nope, same color. So we're going to go, again, from the tip, going to line it up with the focal point. It's going to hit the axis and then go back. It's going to hit the mirror and go back parallel to the axis. So here we go. It's there, and then we're going to try to draw this as parallel as we can. Again, if you are really big on getting things right, you see, you could measure it. I really want a neat copy. You know me about neat, so do the best that you can. So now what we have is 2 rays, and let me label it. This is ray 2, and that's ray 2 as well. Now, I said before, and a student brought this up, and again, credit to Jackson Reed. I always hear questions I've never heard before. And I said, an image is going to be created where light rays intersect. And a student actually said, well, the light rays are intersecting in 2 spots, here and here. And I said, never heard that before. You're right. However, we need 3 rays to define an image, not 2. These are where 2 rays come together. The third one is going to be critical. So the third one is interesting. If you were here for planar mirrors, and everybody was, we were playing with the lasers, we established that there's always one ray that goes into the mirror and bounces straight back at no angle. Just goes in and out. It goes back the way it came. And that's what we're going to have here. And the ray that does this is the ray that goes through the center of curvature. So the third ray is going to go from the tip of the arrow through the center of curvature. That's not the focal point. Center of curvature. It's going to go to the mirror and it's going to bounce straight back. So let's get that lined up. Hits the mirror, goes straight back. And I put a little, that's okay over there on the end. And so this is ray number 3. And what you should notice, again, we have a little bit of error here, but we want to see where all 3 rays intersect. And here we see it's going to be somewhere in this region, right? That's due to my drawing error. That's due to us estimating. We're doing the best we can, but we expect that a little bit. So what I'm going to do, I think it's a pretty good approximation to put that the tip of this arrow is going to be recreated right about there. I think that's a pretty good approximation. And now keep in mind that the image that's being recreated here is not the entire arrow, it's the tip. So if we were to do this on every point along this arrow, what we would get is an upside down arrow at that point. So there's our image. Okay, now we got to do some more measuring. First thing we got to measure, thank you for doing this, my lovely wife, Joanne, Ms. Mangiarelli, helping me out. I really appreciate the help here. Her arms are falling asleep.
No, my back hurts.
Oh, I'm sorry. Okay, well, I'm sorry.
No, it's all good.
So the height of this object is going to be 2 centimeters measured. So I'm coming over here. Height of the object, 2.0 centimeters. Need the image, the height of the image. DHI, height of image. Next thing, distance to the image. Again, we're measuring it from the mirror. That is going to be at about 7.4 centimeters. So 1 there to there. So the distance to the image is going to be 7.4 centimeters. Now, you need to measure it on your own. That's what I get. Okay? My part is now done. Here's what you have to do. These are the questions you have to answer. 1, you have to measure DI. Yours is going to be different because you drew it. You're going to measure HI. Yours is going to be different. You drew it. You need to calculate, this is called the mirror formula. It's a relationship between DO, DI, and F. It says 1 over F, the focal length, is equal to 1 over DO plus 1 over DI. What you need to do is calculate F with this equation and make sure that you get about 5. Our focal length is about 5. So when you put in your DO and DI from the formula, you should get F. Keep in mind, this is 1 over F. So you got to get F. Next, I want you to calculate the magnification. Magnification of this object is high over ho. All right, so is it going to be bigger or smaller than the original object? Is the image real or virtual? If real rays came together, it's a real image. If virtual rays came together, it's a virtual image. And is this object upright or inverted? So you're just going to answer those questions on that paper. Pan out. So that's what you need to draw all that. Then you do your measurements, fill in this, and then that's our first ray tracing for a concave mirror. All right, so thanks, and if you're done with this, you can move on to video 2.